What is the main motivation behind the development of Layerwise Importance Sampled AdamW algorithm?
The main motivation behind the development of the Layerwise Importance Sampled AdamW algorithm is to address the observed phenomenon of skewed weight norm distribution across layers in both low-rank adaptation, LoRA, and full-parameter fine-tuning methods. This skewed distribution implies that different layers have varying importance in training large-scale language models, LLMs. By leveraging this key observation, the researchers aim to simulate LoRa's updating pattern by selectively updating only essential LLM layers while leaving others untouched. This approach allows LISA to bridge the gap between LoRA and full-parameter fine-tuning, enabling efficient training of large-scale LLMs with reduced memory consumption. The idea behind LISA is to sample different layers based on their importance, emulating LoRa's update emphasis without the limitations of low-rank representation, ultimately leading to faster learning and improved performance in fine-tuning tasks.
How does LoRA differ from full-parameter fine-tuning in terms of representation power, according to the paper?
LoRA differs from full-parameter fine-tuning in terms of representation power by exhibiting a skewed weight norm distribution across layers. The paper highlights that LoRA tends to emphasize the bottom layer and/or the top layer, allocating the majority of weights during updates, while the other self-attention layers receive a smaller share. This uneven distribution of weight norms implies that different layers have varying importance in large-scale language model, LLM, training under LoRA. In contrast, full-parameter fine-tuning does not show this skewed distribution pattern across layers. This difference in weight norm distribution between LoRA and full-parameter fine-tuning signifies that LoRA values layer-wise importance differently, which can impact the representation power and learning dynamics of the model.
What key observation led to the development of LISA algorithm?
The key observation that led to the development of the LISA algorithm was the discovery of a skewed weight norm distribution across layers in both LoRA and full-parameter fine-tuning. This observation revealed that different layers in large-scale language model, LLM training, have varying importance. Specifically, it was noted that the bottom layer and/or the top layer occupied the majority of weights during updates, while other self-attention layers only accounted for a small amount. This insight inspired the idea of sampling different layers based on their importance, aligning with the concept of importance sampling. As a result, the Layerwise Importance Sampled AdamW algorithm was created to selectively update essential LLM layers while leaving others untouched, enabling the training of large-scale models with reduced memory consumption. This strategic approach allowed LISA to outperform both LoRA and conventional full-parameter fine-tuning methods by a significant margin in downstream tasks, showcasing its potential as a promising alternative to LoRA.
What are the key contributions of the proposed LISA algorithm, according to the paper?
The key contributions of the proposed LISA algorithm, as outlined in the paper, include 1. Discovering the phenomenon of skewed weight norm distribution across layers in both LoRA and full-parameter fine-tuning, highlighting the varied importance of different layers in large-scale LLM training. 2. Introducing the Layerwise Importance Sampled AdamW algorithm, a simple optimization method capable of scaling up to over 70 LLMs with less or similar memory cost as LoRA. 3. Demonstrating LISA's effectiveness in fine-tuning tasks for modern LLMs, where it outperforms LoRA by 8% to 36% in MT bench and exhibits superior convergence behaviors. 4. Showing that LISA even outperforms full-parameter training under certain settings, indicating its potential as a promising alternative to LoRA. 5. Achieving similar performance gains across different sized models, 7B70B, and various tasks including instruction following, medical QA, and math problems. 6. Providing a memory-efficient training strategy that reduces memory cost and accelerates training speed, enabling high-quality fine-tuning on affordable hardware like a laptop computer. 7. Demonstrating LISA's scalability on large-sized LLMs, showcasing its competitive performance compared to LoRA and full-parameter fine-tuning. 8. Conducting ablation studies to analyze the impact of key hyperparameters on LISA's performance, offering empirical guidance for parameter choices. 9. Showing the stability of LISA's performance across different runs with varying random seeds, indicating its robustness to randomness. 10. Establishing theoretical properties of LISA, including convergence guarantees in convex objectives and the potential for further optimization of importance sampling strategies for enhanced efficiency.
How does LISA algorithm enable training large-scale language models with less memory consumption compared to LoRA?
The LISA algorithm enables training large-scale language models with less memory consumption compared to LoRA by selectively updating only essential LLM layers and leaving others untouched. This is achieved by sampling different layers based on their importance, which matches the idea of importance sampling. Specifically, LISA identifies layers with small weight norms in LoRA and assigns them small sampling probabilities to unfreeze during training. By doing so, LISA can emulate a similar layer-wise update pattern as LoRA while controlling memory consumption. In practice, LISA adopts a sampling strategy that limits the number of unfrozen layers during optimization, thereby reducing memory usage. This approach allows LISA to scale up to over 70B parameter models with comparable or lower memory cost than LoRA. Additionally, LISA's activation memory is even slightly less than full parameter training due to the deletion of redundant activations before backpropagation, further contributing to its memory efficiency. Overall, LISA's selective layer updating based on importance sampling optimizes memory consumption while maintaining effective training of large-scale language models.
What are the hyperparameters discussed in the paper for LISA algorithm, and how do they affect its performance?
The hyperparameters discussed in the paper for the LISA algorithm are the number of sampling layers, gamma, and the sampling period, k. The number of sampling layers, gamma, determines the quantity of trainable parameters and affects memory costs. A higher gamma value increases the number of layers that are unfrozen during training, potentially leading to better performance but also higher memory consumption. On the other hand, the sampling period, k, influences how frequently layers are switched during training. An optimal k value allows for more frequent layer updates, which can enhance performance up to a certain threshold before potentially causing performance deterioration. Generally, having more sampling layers and a higher sampling period tends to result in better performance for the LISA algorithm. These hyperparameters play a crucial role in determining the effectiveness and efficiency of the Layerwise Importance Sampled AdamW LISA algorithm in training large-scale language models.
What are the results of the memory efficiency experiments comparing LISA and LoRA methods?
The results of the memory efficiency experiments comparing LISA and LoRA methods show that the LISA configuration, particularly when enhanced with both the embedding layer, E, and two additional layers, E plus H plus 2L, demonstrates a considerable reduction in GPU memory usage when fine-tuning the Llama 2 to 70B model, as compared to the LoRA method. Specifically, the LISA E plus H plus 2L configuration shows a decrease to 75G of peak GPU memory from the 79G required by the LoRA Rank 128 configuration. This efficiency gain is consistent across various model architectures, indicating that LISA's method of activating layers is inherently more memory efficient. Additionally, the reduction in memory footprint from LISA leads to an acceleration in speed, providing almost a 2.9 times speedup compared to full parameter tuning and a 1.5 times speedup against LoRA, partially due to the removal of adapter structures. Overall, LISA's memory efficiency experiments demonstrate its ability to reduce memory consumption while maintaining high performance, making it a promising alternative to LoRA for large-scale language model training.
How does LISA outperform LoRA and full parameter fine-tuning in the instruction following fine-tuning task according to the paper?
LISA outperforms LoRA and full parameter fine-tuning in the instruction following fine-tuning task by selectively updating only essential LLM layers and leaving others untouched. This strategy is based on the observation of skewed weight norm distribution across layers in both LoRA and full parameter fine-tuning, indicating the varied importance of different layers in large-scale LLM training. By sampling different layers based on their importance, LISA emulates LoRa's updating pattern while avoiding its limited low-rank representation ability and fast learning process. This approach allows LISA to bridge the difference between LoRa and full parameter tuning, enabling effective training of large-scale language models with less memory consumption. In empirical studies, LISA demonstrated superior performance in fine-tuning tasks for modern LLMs, outperforming LoRa by 8% to 36% in MT bench and exhibiting better convergence behaviors. Additionally, LISA even outperformed full parameter training under certain settings, showcasing its potential as a promising alternative to LoRa. Overall, LISA's innovative Layerwise Importance Sampled AdamW algorithm, which selectively updates essential LLM layers, contributes to its superior performance in the instruction-following fine-tuning task compared to LoRa and full-parameter fine-tuning methods.
What are the theoretical properties of LISA algorithm discussed in the paper?
The theoretical properties of the LISA algorithm discussed in the paper include its convergence guarantees in the original loss function. Specifically, for Layerwise Importance Sampled SGD, the convergence can be guaranteed for unbiased estimation of gradients with increased variance. Additionally, for Layerwise Importance Sampled ADAM, there are theoretical results proving its convergence in convex objectives. The paper mentions that if the algorithm runs in a bounded convex set and the stochastic gradients are bounded, the sequence generated by LISA follows a specific convergence rate formula. This convergence rate formula ensures that the LISA algorithm converges towards the optimum value of the loss function. The paper also highlights that LISA aligns with ADAM, optimizing the loss function with a scaled regularizer, further emphasizing its convergence properties in training large-scale language models.
How stable is the performance of LISA algorithm under different random seeds for layer selection according to the paper?
According to the paper, the performance of the LISA algorithm is quite stable under different random seeds for layer selection. The study conducted 3 distinct runs with different random seeds for layer selection using models like TinyLlama, Llama 2-7b, and Mistral 7b with the Alpaca GPT-4 dataset. The results showed that the performance gap across the 3 runs was within 0.13, indicating minimal variance in performance. This small difference in performance across runs suggests that LISA's performance remains consistent and reliable, regardless of the specific random seed used for layer selection.